the motivation is, in this context, the motivation is again interesting. So as I mentioned, this is also the example that I am going to take. There are two examples I will take in this non-real time. And the motivation came again from an unconventional direction actually. So I was working on this PMU as I was presenting, and I went to some conference talking to colleagues that I was excited that we have come up with some pruning algorithm. This is working very well, so much 90% bandwidth saving, etc. And this person was working on smart meters. He was a professor at a university and he has a startup, so they are saying they are using these smart meters for remotely monitoring power usage of different businesses, different food outlets. And what they are doing is that these food outlets told, they want to have better customer satisfaction, and at the same time they want to ensure that they don't burn electricity power unnecessarily. So what that means is that when there are less customers, they should appropriately adjust the power level remotely. Someone should monitor remotely. So they have deployed these smart meters, and then these smart meters are entire data is being collected remotely at some repository, and that company was remotely monitoring and remotely turning on and off different power. I think your hostel management might be happening similarly. Right? So that was, so he was telling that your algorithm that you have developed for PMUs might work there. So I thought, okay, that is good. So let us try to venture. So we actually picked up our problem. That was my starting point. Can our algorithm that we have developed for PMU work in power meters? The first thing that we figured out when we got into the power meter, again there are some interesting power meter data available in the literature. Okay, so there is the MIT RAID dataset, REDD RAID dataset is actually available. Power meters have been introduced, electrical power, I am talking about electronic power meters or smart meters they call. Smart meters have been developed already possibly more than 10 years. The idea that came is that, so what is the purpose of power meters? Power meters purpose is to figure out what is the load consumption, right? So monthly billing, for example. So you should know what is the billing. But what the visualization has been that using these power meters and monitoring the power consumption pattern at a much faster rate, possibly on the order of seconds it will sample, and then collecting that data by the power grid provider or maybe any other company, they might be able to figure out not only power usage pattern over the grid, but also by sampling the power consumption pattern of a location at a high rate, one can actually disaggregate this and figure out what is the power consumption pattern of different appliances. So for example, if my home is being monitored and then if the high sample data is being collected, and then from the monitored data I should be able to disaggregate and figure out what is my consumption pattern of my AC, consumption pattern of my freezer, consumption pattern of my, let's say, washing machine, and so on. And in that process I should also be able to figure out what is the health condition of the devices. So this is very interesting from the service provider's perspective, appliance service provider perspective. So they will be able to monitor the, let's say, my washing machine health. I don't have to call the washing machine company to tell what is the situation. They will be able to collect the data and they will be able to monitor that your washing machine is required servicing, or my compressor of the power refrigerator is not doing well, etc. So these are the motivations, and that motivation led to have these power meters which are supposed to sample data at a high rate. This is a smart meter. This is supposed to sample data at a high rate, and the assignment, practically today, say every second samples are being collected, and these samples are being transmitted to a data collector, this is in power meter context, this is called head-end system, HES. And then they are being eventually transmitted to, let's say, maybe cloud center, and then from the cloud center, maybe power grid provider might figure out what is the load pattern. Some maybe appliance company might figure out what is the appliance health of different houses or the appliance that they have sold, etc., etc. And why the problem is different from what we discussed so far is that this power meter data is not so real time, meaning that it is sampling at a high rate, but this sample data is collected every 15 minutes in today's deployment that we have seen. Every 15 minutes, this head-end system will poll one of the meter and then another meter, and so on. So there are some n meters connected to a head-end system, and head-end system every 15 minutes will send request to one meter and it will collect the data, and this process will continue. Okay. So that is so what that means is that this is collecting sample at a faster rate, but these collected samples are stored locally at the meter, and then whenever a request comes, it dumps the data. So and that is supposed to be reasonably sufficient. Okay. So and the literature in this context is that people are talking about bandwidth saving purpose from the data collector onwards. So what they have done is that there are multiple meters. These meters are being polled by this head-end system, and head-end system is now dealing with the data compression, so-called, at this point, at the data collector point, head-end system. What we are interested is that can we not do this pruning at the source itself? The motivation is the same, that my source is, remember that this is a IoT device, non-real-time IoT device, and this non-real-time IoT device is sampling at a high rate, but data is collected at a non-real-time basis, maybe at regular polling interval. And can we not prune the content here, because if this is wireless connected, this meter will consume much less power for dumping the data without losing intelligence or information content. Okay, so that was the motivation, and this problem had a good resemblance with respect to the first problem that we discussed. This cognitive radio problem that we presented actually. So traffic analysis that we are doing, and we will see that soon. So first of all, although it is a power systems monitoring, power health monitoring, power meter data, but it is quite different from the power health monitoring PMU that we discussed a while ago actually. So literature is basically concentrating on prunability at this point. What we are looking at prunability at the meter end itself. Now by doing that, what we are also imagining that because now this meter is sending much smaller volume of data, so earlier the head-end system was able to monitor, let's say, n nodes. Now it will be able to monitor possibly n prime node, where n prime will be much higher, because the time required for dumping the data from each of the meters will be much lesser. So within that 15-minute interval, it might be able to poll more number of nodes. So that helps us to kind of maybe larger IoT system or massive machine type communication concept could be invoked. Then we are able to connect more number of nodes. So we are looking at the data. This is the data that is available online. This from the MIT data set we have collected actually, and so our immediate task was that given this data set, let us try to understand the data. Okay, so we first tried to plot this data probability distribution concept. So we got a very interesting pattern which is kind of similar to what we observed in our what is that called cognitive radio context. So see that this is my power consumption. So again starting with, because this is a new context to me, I was not aware what all other parameters are of interest. So we figured out apparent power for power meter apparent power is the most critical parameter. Like PMU, I was telling, most critical parameter is ROCOF, rate of change of frequency. So we started with ROCOF, but later on we integrated other parameters. Here we started with apparent power as the primary parameter because our primary interest is to see the power consumption. So we started with apparent power data. So volt ampere, this data set is available from this thing. And then we wanted to figure out what is the pattern. Okay, consumption pattern is looking like quite as spiky. So this is like Gaussian mixture. So Gaussian mixture model that we discussed earlier. See, there are 4 sticks approximately. So our thought is that let us first characterize this data. Characterize in terms of probability density function, and maybe I do it time to time because the data might be dynamic, but for a given data set we are able to characterize, and we are seeing that this is looking like empirical data is looking to be quite spiky. PDF is spiky. So immediate thought is that let us model using GMM, Gaussian mixture model, and then we will try to prune the content as much as possible, ensuring that I am keeping the distance between the empirical distribution and the model distribution as close as possible. Right? Making sense? So this is the first observation, that this data looks to be this. And then Gaussian mixture model, I am going to skip through. Here, instead of choosing K's distance, Kolmogorov-Smirnov distance, we chose actually a different measure. The reason was that, as I mentioned in the literature, there are maybe 1 or 2 more distance measures available. So again, no one dictated us that this measure is appropriate to choose. So we chose in this time this distance measure. The reason is that the literature also suggests that Hellinger's distance below certain value, 0.05, is supposed to be acceptable. Closeness, goodness of fit. There is a definition that below 0.05 is considered to be a good fitness. So that's why we chose this. Again, there is no hard and fast. We could have chosen some other distance. But the summary is that we are trying to model this distribution, and then this model distribution is being compared with respect to empirical distribution using this goodness of fit measure called Hellinger's distance. And see, as you see here, that Hellinger's distance, by going beyond 4 or so, it is not reducing further. So we chose that Gaussian mixture for k equal to 4, that means 4 components is sufficiently good, and other parameter values are given here. So in this case, first objective is to characterize that I have 4, k equal to 4 is sufficient, and corresponding mu values are given here, corresponding sigma j and wj values are. So we have modeled this, and then we wanted to see how the model distribution is fitting well with respect to the empirical distribution. Okay, so far nothing is happening. I have not compressed the data, remember. I have just modeled the data and I am comparing with the empirical distribution. And as you can see, empirical distribution is this thing, and 4GM is fitting very well actually. And this has to fit well because my error measure is not reducing further. So this has to be quite good actually. And we just, for our curiosity, we tried other distributions. Like this was not proposed because this has not been studied in the literature. So we considered other more general Pareto, exponential, GV, remember what is that, log normal, gamma, etc. So we tried to fit, and this is clearly fitting quite well than others. So that is first part. So what I mean is that now I have empirical distribution, and for that I have a model distribution. Model distribution of the raw data. Okay, that is my benchmark now. Using that benchmark, what I will do is, I will now try to compress as much as possible, as long as the compressed distribution remains close to the raw model distribution. Okay, so that is the task actually. So this is further, so this is still empirical level actually, empirical and model distribution closeness. So Hellinger's distance is beyond 4GM, it is kind of saturated. It is reducing, but reducing at a much slower rate. So as a trade-off, we chose 4GM and so on. So that is a secondary question. Okay. And then in this case, because I have a batch of sample every 15 minutes, so every 15 minutes I came to know later, but when we were studying, we were not aware what is the optimum size over which I should do the pruning. Okay, so later on when we were actually implementing, we figured out that this actually every 15 minutes is typical strategy. So this strategy of compression, we have chosen compressive sampling approach. This is again known technique. I am not going to spend time here. So the idea is that I have a single variate. Remember, I am still dealing with single variate. Apparent power is the one data stream, and then using that, considering that I am doing a compressive sampling approach. So I am figuring out of these set of samples, what are the useful samples which are sufficient to carry the information of all the samples. Okay, compressive sampling theory is very well known. I am skipping through. We are running out of time here. So smart meter is generating n samples, and this is adaptive compressive sampling. Why it is adaptive? And we will see that we have actually deployed this in our different parts of the campus, and it actually chooses to decide the compressibility depending on the situation and location. And then it transmits here. So there is a pruning happening here. Instead of SBM based pruning or multivariate SBM based pruning, we are doing compressive sampling based pruning. And at the other end, there is a again known technique, subspace pursuit based technique, which is unpruning the content or decompressing the content. So here I have this compressive sampling based prune content being transmitted, and this transmitted content is much lesser compared to the original raw content, and this low volume data that is being transmitted at the HAS end, I am HAS end or at the cloud, wherever I want, I am uncompressing that content and trying to interpolate and estimate the original stream. Okay? This output is the estimated original stream with some actual values and many other estimated values. So now my question is that at the output I have my estimated data. These estimated data, we will try to construct the corresponding distribution, and we will match that distribution with respect to the original model distribution that I had here, because original model distribution is my reference for our research purpose, and we demonstrate that this much of this achieved. Okay, so here we see here that as we see here, this was I was talking. What is the number of samples that are required or that are giving us sufficient prunability? So as the number of samples are increased, so batch size is more than 500 is not benefiting further. So you see, this is the error rate is not reducing further. So this is telling me in some sense that my batch size should be this much, because my error rate is the supreme actually in terms of compressibility, and corresponding bandwidth saving is about 39.9%. So we chose this batch size to be 500. So 500 in this 500, 600 actually, n equal to 600. This point is 600. 600 is 15 minutes. Okay, so it is 10 minutes. Yeah. So for in our case, because as I mentioned, we just from our data the rate data set, we consider that these 10 minutes is giving me the optimal, and by increasing this thing it is reducing a little bit further bandwidth saving, but it is not helping much. So okay, so I think crux I have already told, and now you can see that this apparent power, my actual data versus reconstructed data are matching pretty well. So that kind of tells that we have not lost the information, but more importantly, here this plot is more important, that now empirical versus 4GM reconstructed versus 4GM model. Okay, 4GM model, 4GM reconstructed, they are are pretty much overlapping, so that kind of visually confirming that we have not lost information. But more importantly, the error that the RMSE content that we see, I think we have this RMSE that is happening. So this is 0.0065 and so on. Okay, so I think summary I have already mentioned, and then we have compared with a technique called this thing, reasonable load data compression, RLDC. So basically they have, so the company that I was talking about, they have taken this lossless compression technique. They are collecting the data every 15 minutes, they are zipping the content and then transmitting. So what we have chosen that instead of zipping, we are using this compressive sampling technique, and this is lossy, but this loss level is within the given tolerance margin, and that is giving us significant benefit in terms of. So RLDC is here versus our approach is bandwidth saving is significantly higher if the data collection interval is smaller, and as the data collection interval is larger, then it is actually losing anything. But major advantage of doing this our technique is that these are some other possibly. Yeah, so this is one interesting observation that our technique, this lossless technique, is dealing with the channel error much smoothly compared to the other approach. So RLDC, once it is unable to track the data, it actually the error rate goes significantly high. So this is apparent power, actual data, apparent power sampling, and memory. Yeah, this is the RLDC approach. This is the bottom one. Reasonable load data. Reasonable load data correction. This is actually if once it is unable to track, it falls apart actually. Whereas in this case, it is following smoothly for a given error rate in the channel actually. Okay, I think summary I have mentioned already. So basically now again similarly for the single variable we started with. Then this looks to be quite implementable and much easier than the PMU context. PMU is much more complex device compared to this. So we have actually we tried to implement this thought in our actual meters. We bought some meter, basic analog meter, and then this analog meter output some via RS485 bus. This data is being transmitted, collected to a Raspberry Pi for development purpose. So actually, of course, there is a data converter here, and then this RPi is where we incorporated we attempted to incorporate our single variable. Now that there are again one direction that appeared here is that because this meter is collecting multiple other parameters, like I was talking about PMU. It is so the question is should we apply this compressive sampling approach for individual streams individually, or should we do cross correlation exploitation? So we did similar approach. So in this case, because this is non-real time, so this batch of critical data that we have is 8 parameters. So we pass through PCA, and then at the PCA output in a different dimension. So we picked up the most important components with the variance certain above certain threshold, and on those important components we are applying our compressive sampling technique, and that is the transmission here. And further similar inverse thing is happening. So at the implementation we have considered these approaches. Okay, so these some benefits actually. So these up to 50% versus 90% bandwidth saving with respect to ACS and no compression. So ACS is the adaptive compressive sampling. If we apply on individual streams versus if we apply together, we are getting some 50% benefit. and if I have no compression, then with that we have significant limit. And the construction error is kept with the 10⁻³ error. So this has been actually implemented in different parts in the campus, and to figure out. So right, yeah, yeah. So I give a pause here, and this is another module, sub-module. And are there any questions on the these things, smart metering related problem? Yeah, is it?
That's a very important issue, the adaptive multi-rate setting. And usually, when you define multi-rate, do you consider more than 2, maybe 3 or 4, or just 2?
No. So this is as I mentioned, my system is doing actually that diagram that I showed is for conceptualization, but PCA does that job. So it will figure out this thing, this is your. So I go back to that diagram here. So this PCA, after passing this data set through the PCA, and if I order the data with respect to the variance, then I see that the first one has high variance, second one has possibly higher, a little bit lesser variance, and so on.
I think I think, how about the compression? When you say the multi-rate data compression,
multivariate data compression. So what I mean is that we are compressing at 2 stages now. At one stage, we are throwing away some of the streams. This is the PCA outcome is doing that. And the second stage, out of the remaining streams, I am doing temporal compression.
So it's in a further stage. So when you say that, this is a 2-stage.
2-stage, yes. Yeah. No. So multivariate. Multivariate. So these are multiple variables.
Yes. Different variables.
Yeah, different variables actually.
Yeah. Thank you for clarification. So, do you have a question? Doing similar work for the smart grid and network?
Yeah, any question, curious question, because that is important for me to be sensible, whether I am making sense. And as I mentioned, this work is, for me, that is very interesting because I don't need any high-end system actually. So we simply started with buying some RPIs and implemented, and once we are able to implement, we have now developed our small cards. Actually, we have implemented using these, what is it called, this ST microcontroller. I think ST32, I forgot the microcontroller specification exactly. So we have actually, around that microcontroller, we have designed our peripherals, and then that microcontroller is doing the entire job actually. Okay. So again, power consumption part we have not emphasized so far, but we are going to do that offloading of the power consumption aspect by offloading the task to the HES. So this is actually a very interesting problem that we are pursuing. We have done that from the smart sensing context. I will present later. So you have multiple sensors. Okay. So this is let's say power meter 1, power meter 2, etc. So these power meters, all these power meters compressibility could be offloaded to the HES. So HES can do them individually for each of them, or now HES also can do a second level of what is that called optimization, considering that can I implement the same what is that called compressibility to the other instead of actually doing the process. So we are actually exploring that part from the sensing perspective. And this is reason. For example, if the 2 meters, so if there are let's say one computer room, one computer lab, and another computer lab. This computer lab has one smart meter, another computer lab has another smart meter. So naturally, these computer labs are actually generating computer related power consumption only. So they are very correlated in a sense actually.
There's a problem that for the research problem we do together with Ashtash regarding the dual power system, which monitoring the traffic and also monitoring the.
But for the problem we haven't been investigated regarding the dual power system, like the smart grid and the base station power management issue. The base station power management issue consider both the energy consumption, the variation distribution, and also the traffic variation. So right now we consider these two different networks. Actually, then there are three dimensions variable, right? When I say variable, it's actually first variation is from a base station perspective, that it's energy consumption profile. Second thing is traffic, and traffic arrival and departure behavior. That's from base station side. Then for smart grid, you also have two very different variables. One is the energy harvest behavior and how distribution in terms of the time. And on the house, when he make a transaction and they will sell the energy or will buy the energy, that's another profile. And then we formulate a problem as the cost optimization issue to find using the model decision process to make a faster base investment, for example, the
design optimization.
So the GEO is doing some other the work to extend from this concept. So I think that today's presentation I have learned so far helped me a lot to understand the fundamental, the background. Beyond that, we can have some more algorithm developed. So, for example, that how can we more microscopic design for example, where we put for example, the meters and to get the information and how to optimize this to manage this dual network for the best investment in terms of energy and I would say the energy per carbon, yeah. So it's not the energy per bit, it's the energy per bit per carbon. So based on this new matrix to do this work. So what do you think about this?
Yeah. So this is actually the next module I am going to talk is very close to what we are discussing.
Okay.
So exactly how do I measure what is the source generation nature of the
energy?
Yeah. So I think this is a good way to defining this new what is it called energy parameter actually. What is it called performance index, new performance index, which is energy per bit per carbon.
Actually. So that's why I suggest that you should look at this metric to see then how other tools can be incorporated in formulating your research problem.
Actually, this WCNC Professor Theodore Rappaport was giving a keynote actually.
Ted
Rappaport actually. So I forgot the terminology. Actually, he was suggesting that a new term for this system efficiency is coined, not anymore with respect to the energy per bit, but very similar to what you are talking about actually.
Thank you.
So I think I have noted somewhere. I'll forward that actually to you. I have some slides on my mobile also. Okay. So I'll forward it.
Right.
So this is so the next discussion that I am going to have, this is actually a very nicely overlapping with respect to what I have discussed so far and how it is bridging the next level actually. So what we have is So this problem genesis is ML-aided power signature analysis. So this problem actually came from industry. So we have a service provider, telecom service provider called Airtel in India. So it is one of the largest, if not the largest service provider, telecom service provider. So they have a peculiar problem, and peculiar problem possibly with peculiar to Indian context. So in many places we do not have the constant power grid supply. Power failure happens, and there are some remote places where there is no supply. I think that possibility is very less. So all places have power connection, but not necessarily 24-hour power. So somewhere maybe 12 hours a day power failure, somewhere 6 hours on average, etc. And let's say in Delhi, maybe 5 minutes power failure a day, etc. So for that one, because if your telecom service is very critical service, they cannot even tolerate 5-minute failure, right? So they have to have a backup. So what they have is all base stations, they have diesel connectivity correspondingly. So there will be a diesel generator as a backup, and this diesel generator will automatically turn on when the power grid failure happens. In between, of course, there is a battery will run for, let's say, 5 minutes or so, and then within 5 minutes if the power doesn't come, then diesel will automatically turn on and it will draw power from the diesel until the power grid comes back. Okay. And also there are places where there are some ambient solar connectivity. Wind may be there, but at least solar, I know in Noida, for example, they have deployed solar connectivity. So the power, this is very close to what Asutosh is doing, but problem definition is very interesting, very different actually. So a base station today is connected with grid, with diesel, and also with ambient power. Ambient would be solar, wind, or anything else. Okay? Now, for the service provider, the problem is today the service providers do not maintain the sites. Okay, where they deploy a base station, it is given to another third-party company, and that company will give the site management is their responsibility. Diesel they will manage, they will maintain AC, etc., and they will give monthly bill that this is your this month's bill and so on. And Airtel says that the bill that they are paying is much higher they anticipate than they should be. They are saying, okay, these many hours I have run diesel and so on, but possibly that is not the failure rate, power failure rate that we are aware of. But Airtel says they have no way to challenge that provider that what should be the actual bill. Okay, so they came to us saying that can you somehow monitor, and now the other problem is that these sites are maintained by one company. In India, this is called one company called Indus Tower, and this company will be providing service for Airtel in the same site, another company Jio, another company Vodafone, and so on. So one site is managed for multiple service providers. Okay, so as a result, Airtel cannot tell, okay, I want to deploy one gadget. What gadget that Airtel do not know yet, but one gadget, so that I want to monitor myself. Because as if the Airtel cannot also tell them I am suspecting you, right? It's like a business relation actually. So Airtel came to us saying that, okay, our safe point where you can measure, you can put your gadget is the power box from where I am drawing power. So that is where I have a lock, can keep. So you can measure the power consumption pattern at that point, and that point is giving them minus 48 volt supply. Minus 48 volt supply is going to their Airtel radio and whatever OMC unit. So minus 48 volt supply point that is going to Airtel devices, Airtel equipment is what is my measuring point. So they are saying that monitoring the DC power, can you capture the source of power? That whether this DC power is coming from grid or solar or diesel or battery. And then if that is possible, then one can calculate simply by knowing what is the consumption and what is the cost, right? So that was the interesting problem that was given to us, and we took interest, and now the challenge in this case is that, so you see the primarily predominantly AC power conversion, step up, etc. And so in our context, and the one point is what I explained. What is the company's interest? Company's interest is to identify. That's why we call source signature analysis. So this is actually more generic term. I will come to tell why this is generic. So their objective was the source identification. They are saying, can you give us a gadget which will monitor the source of power? And let's say over the day, these source A, source B, source C, etc. Can you give us this? So we took up. So what we did, so the problem is that, so I think I have a diagram and go to that. Yeah. So this is the situation actually. So DC power management, and this is multiple sources. These example 3 sources, and these 3 sources are going to the utility. The utility is, let's say, that service Airtel, and we want to monitor this air at this point minus 48 volt line. And we name these as ISID, input source identification module, or I call later that PSIM, power source identification module. And this power source identification module has to monitor the sources. But these sources are not just directly connected. These sources are, for example, solar is already generating DC. This is possibly grid. This is possibly diesel, and they are all passed through a what is called switch mode power supply and a battery bank. And this exact order I forgot. But the signatures that are being generated from different sources are kind of smeared by the SMPS, because all sources are passing through the SMPS. So our main challenge, that's what I mentioned, the source masking and rectifier influence actually. Source masking is because the SMPS has its own high sampling rate of capturing these data, and then it is giving a stable data. The SMPS functionality one can look at, and so whether there is any signature left after passing to the SMPS, that is the challenge that we took up actually. Okay, so yeah, so basically existing works do not address this DC signature, and there are some papers. In fact, again my power background student actually helped here. We figured out that power source quality identity is actually a major problem. In fact, many companies are interested in monitoring what power we are supplying to the appliances, because if the appliances get some harmful signatures, harmful harmonics, these appliances could be damaged. Okay, so it is very important to measure the quality of these things. Okay, now this monitoring is primarily done from the AC source perspective. Okay, of course we could still think of using this thing, but we have. So from the DC perspective it has not been studied, but the problem is interesting. This is the source quality. Okay, so required analytics for identifying the extreme frequency component and clustering and signal processing have promised in harmonic analysis. So what we are looking at is that this signal processing technique actually, and nicely this also has been aggregated or clubbed nicely with respect to ML. I'll explain later. These methods do not address the source identification from the DC bus. So the key point is this. Okay, so this we have a conference paper, we have a patent applied, we are applying for another patent soon on that. Okay, so rest of the approach is apparently straightforward. I have already motivated sufficiently. So what we have done is that at this point, I think I will skip through because my time is already quite fast. Yeah, so I'll go to directly over here. This is our emulation in the lab, and possibly Professor Wang, you might have seen, Asutosh might have explained this thing a little bit. I have a video, small video, if I have time I can show. So what we have done is that this is the so to emulate the system, we have created our own lab setup, And lab setup is actually much more challenging actually, because the power source output that is provided to the electrical supplies, what is that called, this base station. This is much cruder compared to the power that is fed to the AC computers actually. These UPSs are much more refined. So anyways, so this is my the one UPS. This is one UPS, and then so okay. So this is the module here. So anyways, so we have two lines. Maybe I will draw this here. So we have considered this is the DC line minus 48 volt and 0. And what we have done is that at this point, so this is we wanted to do non-invasive as much as possible. So this point is anyways connected via some screwable contact point. So at this point we are measuring this voltage, and here we have used a Hall effect sensor for measuring the current. Okay, so these are the three parameters that we are interested in. The current by the Hall effect sensor, which is simply clickable, and this voltage, and these analog points are passed through a high rate ADC that we have incorporated here. So we are sampling at a very high rate. So these ADCs are allowed to sample at as high as 20 kSPS, 20 kilo samples per second. And we by doing trials and some analysis, we figured out some 1000 kSPS in our case. 1000 SPS is sufficient. So 1000 SPS it is sampling. And by doing that, we have been able to figure out that these signature analysis from different sources, these signatures of the power sources are actually captured. One can differentiate the signature of the sources by sampling at a high rate. That is a straightforward case. But the challenge is that what we considered and we studied, that when we vary from one UPS to another UPS, one SMPS to another UPS, this signature does not necessarily remain the same actually. So what that means is that this the analog signal that is being sampled, the signature that we collect has to be learned to identify the current devices that are employed, and then it will do the prediction of source identification. So these are deployment related details. I'll skip through. So basically, by doing a simple learning technique, we are able to identify the device characteristics, and basically when the implementation deployment stage for a few seconds, possibly maybe less than 2 minutes, we are able to capture the signature and then distinguish the sources by switching over from multiple sources, and then subsequently it collects the data and then it distinguishes them. Okay, so that is all actually. So with respect to the case, the other aspect is that this current input is not otherwise required for the pure source identification. This voltage input is sufficient. Current signature is has come out to be very handy to figure out the signature of the power quality. Okay, so by measuring the current as well as voltage, we are able to capture the power quality, and that is actually a byproduct for us. Now we are not only able to identify the source identification, but also the source quality. That is what was the original name I was talking about, source quality monitoring. Okay, so you see here we have used this LDA as the technique to answer this question of AIML. You see so data set creation, and instead of using PCA, we figured out that LDA is being better, and then we use this SBM to eventually classify this. So this is the technique that we considered over here, and this, yeah. Okay, so there are, I think I will not spend time on the takeaways. So as I mentioned, that we have taken actually examples for these non-real-time and real-time IoT, but they are actually generalizable for multiple other contexts. That is customizable. And why I was telling this last module that I just discussed is a very nice transition to the next module that I'm going to discuss. Is that this module is we have entire control. So we are currently sampling at certain 1000 SPS, but because we have our own control of what is the sampling should be, so we can actually do smart sensing. I will come to that in immediate context actually. So what I mean is that so far the two modules we have discussed, real-time IoT and non-real-time IoT, these are backward compatible in the sense that if I am given a high sample data, how to smartly prune the content or smartly identify the signature of the source, we have figured out that. And the last module is because this module we have developed, so we have the capability of not necessarily generating the regular samples. So we can generate samples at an irregular interval also. So I will come to that part in the subsequent discussion. Okay, so yeah, so proposed techniques offer resource efficiency at multiple fronts, for example, energy, bandwidth, storage requirement, and then we have actually a nice connection with respect to some massive IoT. In fact, I have not presented any work here. So, so far I am talking about IoT node level actually. So this can be taken nicely to the access level. We have one PhD student has graduated in that direction actually. 5 minutes.